Hello, today we're going to learn the remainder theorem. But in order to understand the remainder theorem and all types of what we call Euclidean division of polynomials, and that may be a scary name, but it's actually not too hard of a concept. In order to understand it, we need to have a solid understanding of what division is in the first place. So let's go back to, grade 4 when we learned how to divide using long division. The important thing to realize is that there are four main parts to division. You have your divisor, your dividend or dividend, I actually don't know how to say it, remainder, and your quotient. That's really all there is to it, but how can we write this all together? That's what I have on the next line here, and we have the same four parts, the dividend, quotient, divisor, and remainder. We can say that the dividend is equal to the quotient times the divisor plus the remainder. And it turns out you're always going to have a unique expression in terms of the quotient, divisor, and remainder. And you might question me, because here's a counterexample. What about 7 times 4 plus 5? That is indeed 33. It indeed has this divisor, this quotient, this remainder. So we need to add another restriction. We need to say that the remainder is less than the divisor. Because right here, if we said the remainder was 5, that's not okay because we're not done dividing yet, are we? So the remainder has to be less than the divisor, and with that condition, we know that we always have one unique division here that has the product of the quotient divisor and the remainder. And once again, I need to stress this, the most important part is that the remainder is less than the divisor. And this is going to extend when we look at polynomial division. So this assumes that you already have a pretty good understanding of polynomial long division, or at least how to do it. Now, once again, we're going to say that there's going to be a unique quotient, divisor, and remainder. But we need to have a similar restriction. We need to say r, or rather the degree of the remainder, is less than the degree of the divisor. Because let's say we had a quadratic here, and we were dividing by something linear. That means we're not done dividing yet, because the quadratic could further be divided by the linear term. So using this restriction, and I hope it makes some sense, we know that you're always going to have a unique product of, here's your dividend, here's your quotient, expressed with a q as you might have seen, maybe a little hard to read. Over here, we have the divisor, and finally we have the remainder. And as you can see, Euclidean division of polynomials has the exact same four parts we're used to with numbers. So the remainder is here. You can try some division problems for yourself now, and notice that you always have a single answer, and your remainder, or at least the degree of your remainder, is always going to be less than the degree of your divisor. And really, that's all you need to know to understand what comes next, and that is the remainder theorem, for real. So here we go. This is the remainder theorem now. Over here, we have the polynomial equal to, once again, those four parts. We have the dividend, we have the quotient, the divisor, and the remainder. And now we're going to say, what if the divisor is this monic linear term here, or rather monic linear polynomial? And what does monic mean? It just means the leading coefficient is 1. So, what if d of x is just x minus a? We're going to make this substitution and say p of x must therefore be q of x times x minus a, that's our new divisor, plus r of x. But look at this restriction here, because we know there needs to be one unique way to divide. We need the degree of the remainder to be less than the degree of the divisor, because if the degree of the remainder is equal to the degree of the divisor, we could still divide. If it's greater than the degree of the divisor, we could still divide. So looking over here, think about it. If r was linear, so let's say mx plus b, a line linear, we could still divide, right? If it was quadratic, we could still divide, which means the remainder has to be a constant. So it could be 1, 2, pi, just some constant. But if it's a constant, that means it's actually independent of x. And we can say that P of x is actually Q of x times x minus a plus r. And you notice that I don't use the function notation because we just said that r is a constant because of this restriction here. It's not dependent on x. So it's either degree 1 or degree 0. Sorry, not degree 1. It's either degree 0 or the 0 function itself. And in either case, it's not a function of x. And the reason I've done this is because now, look what happens if we evaluate our polynomial at a. So we plug in a, and what do we have? We have q of a times x, we replace it with a, we have a minus a, and last of all, we have plus r. And this is why I wanted to show you that r is actually independent of x, it's just a constant, the remainder. Because right here, a minus a is 0. 0 times anything is still 0. So finally we can say P of a is equal to r. So what does this actually mean for us? It means, well, this is our remainder theorem stated really clumsily. Let's be a little more formal with it. What it means is that if you were to divide a polynomial by x minus a, you get a remainder of r. And that remainder is also obtained by evaluating the function at a. So the value of a polynomial at a is the same as the remainder when it's divided by x minus a. Now we're going to look at how the remainder theorem holds true. So we looked at all of the algebra, looking at all of those letters. We saw a proof, but it's all abstract. We haven't actually tested it out. I hope testing it out will show you that, in fact, there's always going to be a unique division. You're always going to have a single possible remainder, and the remainder theorem does also hold true. Today we're going to use polynomial long division, and for understanding, I think long division is superior to synthetic division. Although synthetic division is very fast, it's a nice algorithm, it hides everything from you. Polynomial long division shows everything, and it's quite familiar because the process is just like what you learned when you were using long division of real numbers. So we have x squared plus 2x plus 1 divided by x plus 3. And I'll go through this a little quickly. We have it going in x times. We need to multiply, so we have x squared plus 3x, and subtract it. We subtract x squared minus x squared is 0. 2x minus 3x is negative x. Then we bring down the 1. X plus 3 goes into minus x plus 1, negative 1 times. We multiply, and we have negative x minus 3, and once again we need to subtract it. Subtracting that, negative x minus negative x is 0. 1 minus negative 3 is 1 plus 3, which is just 4. And right here, that's our remainder. So in theory, by the remainder theorem, the remainder that we got here, a remainder of 4, is also going to be the value when we evaluate p at a. So here p of x was x squared plus 2x plus 1, and we're dividing by x minus a. And a, as I've shown here, is negative 3. So let's test this out. P of a is p of negative 3, and we're just going to plug it in wherever we see x. So, we plug in negative 3 here, and right there. And looking at this, all we need to do is simplify, and in theory, we should get the same remainder that we got right over there. So, 3 squared, or negative 3 squared, is positive 9, minus 6 here, plus 1. This is 3 plus 1, and amazingly, look at what we have right there. That's 4. That is the exact same remainder. So although this was just one instance, I hope you can see that indeed the remainder theorem holds true, and that's how you use it. That's all there is to it.